This is FE Peer Review, the Flat Earth Peer Review channel. The date is August 23rd, 2020. The video in review is titled Flat Earth Science Lesson 1, The Greatest Evidence for a Flat Earth. The video is by Kyle Adams. This is a response to Lesson 1 in Kyle Adams' video series. In it, he sets out the basis for his entire research into Flat Earth.
Let's ask this question. What is the greatest evidence for a flat Earth? What do we found ourselves on? The greatest evidence is the observation of a flat Earth. And that is why the Flat Earth Institute of Science exists. We're not talking mountains, of course. But when we look out at an unobstructed horizon, we can observe it is flat. We can find observation after observation of this. No matter how high you fly, straight horizons are what you see.
I quote, "What is the greatest evidence for a flat Earth? What do we found ourselves on? The greatest evidence is the observation of a flat Earth." And he continues, "No matter how high you fly, straight horizons are what you see." This is the key question, the foundation of the hypothesis and the justification for the entire video series. I will ask and leave unanswered for the time being two questions. What if this foundational observation is fundamentally flawed? Does the weakness in the foundation potentially undermine the strength of the entire structure built upon it? Now we will move into some related questions worth considering. If the Earth were indeed flat, how would it appear to us? I did a video exploring that question and we will come back to it later. If the Earth were not flat, might it still appear flat? Would we be able to see the curve? Let's start by talking about scale. To do that, we need to introduce some basic geometry and also briefly discuss the human eye and camera lenses. This all gets to the word observation, as in the greatest evidence is the observation of a flat Earth. This is wrong picture. One moment. Here we are. This is an eye chart used by ophthalmologists that shows the typical healthy human eye's ability to see peripherally. A normal healthy human eye has what they call near peripheral vision of approximately 60 degrees. In this zone, you can stare fixedly at a point straight ahead of you. Imagine you're at the center of all these this circle here, and you're staring fixedly at a point straight ahead. Within this zone called near peripheral, you can see detail without taking your eyes off of that point fixed straight ahead of you. Beyond that, where it says mid peripheral, you cannot see detail, but if you keep your eyes fixed straight ahead, but you can see motion. We're quite good at seeing motion in that mid-peripheral zone. All you have to do is extend your arms out to either side of you and wiggle your fingertips, and you can easily see your fingertips wiggling, but you will have a hard time seeing any detail of your hands. Finally, far peripheral is beyond what most people can see unless they actually move their eyes from side to side. So practically speaking, the near peripheral is the area within which we can see clearly. Without moving our eyes, we can grasp all of what we see in one fixed image. Now, in nature, in going about our daily lives, we're constantly moving our eyes and constantly moving our heads and gathering visual imagery from a huge, basically 360-degree field of view, which our brains are assembling all of that visual data into the perception of an entire three-dimensional environment. but in reality, what actually strikes our eye at any given moment is quite limited. That will come back. We will be relying on that when we get to looking at some of the geometric models that help us to understand the scale of what we see when we look at the world around us. This chart is from Panasonic, and it's a very convenient chart that relates various camera lenses to the human eye's field of view. So you'll see 50 millimeters and 35 millimeters. The 50 millimeter camera lens, if you come down below, you'll see it says 45 degrees. That represents the field of view of a 50 millimeter lens on a 35 millimeter camera. Standard 35 millimeter camera with a 50 millimeter lens has a 45 degree field of view. And the 35 millimeter lens on a 35 millimeter camera has a field of view of 64 degrees. So the natural human field of view falls within that range, falls between these two. And on the little row of pictures below, each of which is using a different lens, you'll see where it says 50 millimeter lens, normal view seen by human eye. So that gives us a relationship between the human eye and the camera lens. This is essential when we talk about any imagery that we're seeing online. And I want to go to this next page, which is a blog entry written by astronaut Ed Lu back in 2003. He was on the International Space Station, and he wrote this blog entry. That's him there. And he illustrated it with photos that he personally took with his own camera. In this first photo from the ISS, we see a very pronounced curve on the horizon. And if you've looked at enough of these photos, you'll know right away that this curve is the result of a very wide angle lens, that the actual curve that would be seen from the ISS is nowhere near this much. Now, if you were to actually read the caption below the photo, you'll see at the end of the caption, Ed took this view of the big blue beach ball using a wide angle lens. And at the bottom it says June 13th, 2003, 16 millimeter lens. Going back to our Panasonic chart, a 16 millimeter lens is way over here on the far left. Very wide field of view, well beyond what the human eye can see when it's looking at a fixed point straight ahead, which accounts for the extreme curved distortion that we see in this photo. However, if you continue going down his blog post, there's another photo which has a very distinct curve to the horizon, but nowhere near as much as the previous. And if you read the caption, Ed took this photograph, etc., July 11th, 2003, with a 50 millimeter lens. So now we're using the 50 millimeter lens, which according to Panasonic is the normal view seen by the human eye, which also matches this chart here as approximately fitting within this near peripheral zone. In fact, a little bit narrower than that, so more precise than what this chart shows. So let's see, for a more detailed discussion of lens distortion and how it can be accounted for in observations, we have a video by Wolfie6020, which I will just point out here, and I'll play the first few seconds, but I would definitely encourage people who want to explore this aspect of the subject further to watch Wolfie's video. He's explaining here the kinds of distortion that become apparent with different types of lenses.
So this will be a quick video looking at the type of distortion that we can experience in a camera lens, specifically barrel distortion and pincushion distortion. Here you can see two grids. The one on the left is barrel distortion, where the grid squares appear larger than they do in the corners. With pincushion distortion, it is the opposite. The grid squares at the corner of the frame appear larger than those at the center. And this needs to be considered if we are using an image to determine the size of an object, because for a given size object, if we have pincushion distortion, it will appear larger if it is towards the edge of the frame than when it is closer to the center.
In light of the above, we can reasonably say that humans are able to see detail in a field of view of around 60 degrees, and that if what we see does not show barrel-type distortion within that visual frame, we are seeing accurately what is in front of us. The same applies to photos within those same parameters. On that basis, I've made some geometric models that explore the questions we started with. If the Earth were not flat, might it still appear flat? Would we be able to see the curve? And I'll add to that, would we have to get up to some minimum height or elevation above the ground to see it? So we're going to dive into a little model here that I've created in a program called SketchUp. And it's a model of the Earth as a sphere to scale, and it's an exploration of how much of the surface we would be able to see from various elevations. If the Earth is a sphere and we're at a certain distance above the surface of it, how much of it can we see? And in particular, the horizon. How would the horizon appear to us? So this little diagram here is a basic geometric diagram I want to show you that was the basis for the whole construction of this model. If you imagine the large circle is the Earth, then this distance up here called h would be the height of the observer. The horizontal line moving to the right would be the eye level of the observer, and the line connecting the top to the tangent would be a line of sight from the observer to the tangent of the sphere. And that would be the horizon on a globe Earth. If it were a perfectly smooth sphere, we're not worrying about mountain ranges and stuff like that. You're on a boat out in the middle of the Pacific Ocean. You're looking out in all directions. The tangent between your eyes and the sphere comes out a certain distance. Now, if we take this other diagram here in the middle, imagine that you're at the center point and you're looking off to the right. That same distance I'm showing with the dashed line, that defines a circle, which is the horizon that you see in all directions when you're standing on your boat in the middle of the Pacific. Now, if you're looking in all directions, you'd see a circle up like a flat circular plate. But if you were to stop and look fixedly in one direction, let's say to the right here, your field of view, based on the limitations of the human eye, would be something like this white wedge here. And so you would see this much of the horizon. Now, we're looking at a top-down view. So the question is, would this horizon that you see appear as a curved or a straight line? And that's what we're going to explore next. So here's the overall model. And what we see is this big circle represents Earth. And these additional circles, 1, 2, 3, are different heights above the Earth. The first height represents 300 meters, or approximately 1,000 feet, which would be the height of a very tall skyscraper. So if you were to go up to the top of a... Did I get that right? No, excuse me. This first line represents... This one here represents 10,300 meters. That is approximately the height at which an airplane flies, a commercial airliner flies. So if you were at 10,300 meters above the surface of the ground, which by the way is this mark right here, this would be the surface of the sphere that you would be able to see from the airplane. The second circle in this ring is at a height of 39,000 meters, which is roughly 120,000 feet, and this is the height of the weather balloon that Mr. Sensible is going to be sending up in a few days. I am going to leave a link to his video in the description. It's a very exciting project he's doing, sending up a weather balloon with a camera specifically designed to not distort, to not have barrel distortion. So he's sending his camera on a weather balloon up to a height of 39,000 meters, and that's going to capture a surface area of the Earth like of this size. And finally, the third circle represents the surface seen by the International Space Station. So we have the height of the space station above the Earth, right, where these two lines come together. That's the height of the space station above the Earth, and it sees a tangent out to here, which means that would be the space station horizon. So now what we're going to do is we're going to look at a view from down at the 300-meter elevation. If we were 300 meters above the ground, that would be your skyscraper. That's this line right here, this little dashed line where I'm circling. We're going to be looking off towards the right along that red line. That's going to be our line of sight. And I've drawn out here as a marker an object with 10 divisions in red and green. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're going to be looking towards this block over here, and we're going to see that some of it is not going to be visible because our horizon is going to be blocking the lower portion of this. So I'll move to that view now. So you see we can see 2, 4, 6 of the 10 blocks. We're looking straight off towards that little tower of red and green, and a portion of it is hidden below the horizon line. And if you look at that horizon line at a height of 300 meters, it looks basically like a straight line. There does not appear to be any curvature visible when we're looking straight, eye level, no curvature visible on the horizon line. So that's in this model of the Earth, which is done to scale, at 300 meters or 1,000 feet above the surface of the ground, there would be no visible horizon. There was our tower. And we were not seeing any of these lines in our view because our horizon line is in here somewhere. Now we're going to, I'll go back to 300. And now we will go straight up, and we're, as if we're climbing up to the height of a commercial airliner, 10,300 meters. And as we climb, you'll see that more of this tower becomes visible. However, the entire tower is still not visible. We're still missing a little bit of the red one and the bottom green one. And if you look very closely at your screen, it may be that you can see a dashed line running across the middle of the screen here. That is a visually straight line connecting one edge of our field of view to the other edge of our field of view. So if you were to outstretch your hands with a string and pull the string taut so that you had a straight line as a comparison, there's a very slight there is a very slight curvature visible on the horizon if you have that straight line to compare it to. Now, without that straight line to compare it to, I don't think anybody would be able to see this bit of curve. Hopefully you can see it on your screen. However, with the straight line, it's quite clearly visible on my screen. Now, this is commercial airliner height above 10,300 meters, so around 33,000 feet above ground. In order to see this from an airliner, you would first of all have to have your full field of view of approximately 60 degrees, which those small windows don't really provide. The windows themselves tend to be in poor condition, scratched, fuzzy. And finally, you rarely have a completely unobstructed horizon. At 33,000 feet in the air, 10,300 meters in the air, you're not that far above the clouds. It could be a few thousand feet to maybe 15,000 feet below you. So any clouds that would be there would be substantial enough to obstruct the horizon line. So from an airplane, in theory, a perfectly clear day, you would be able to see the curve of the horizon if you had a straight edge to use as a comparison. I'm going to navigate back out of there, and that gives you an idea what we were seeing. That was our horizon line. and we were able to see most of the tower beyond it, but we were missing the bottom green and a little bit of the bottom red. Now we'll go back to that view, and then we will climb straight up, and you will see the entire tower become visible. This is now 39,000 meters, which is going to be the height at which the MAGE balloon project goes. And now we see the horizon line at 39,000 meters. That's 120,000 feet roughly. There is a very definite curve in the horizon, which we do not need a comparison straight edge to see. However, I have drawn in a line that visually is a straight line connecting the two edges of our field of view to provide that comparison, and you can see clearly the curvature here. Now you might find it interesting to note that what appeared to be a straight line connecting those two edges of our field of view, that's this here, this arc here. In order for it to appear to be a straight line, due to it being seen on a curved surface, we're actually looking at something that has an arced shape. Now let's go up again to the height of the International Space Station. Now that's a big jump up. We're going from 39,000 meters all the way up to 408,000 meters, which is, I think, around 250 miles, 408 kilometers. So we will now go up to, and we're going to run into a little problem when we do this, because you may have noticed, let's go back down from the very bottom and look. There was our first skyscraper elevation. Then we moved up the airplane, and notice that not only are we seeing farther, but the horizon is dropping relative to the center line of the screen here. We'll go up some more, the horizon will continue to drop down. Now when we do this again, we're going to find that it drops right down below the bottom of my screen when we get up to the ISS level. And that's because the angular drop from the horizontal line coming from my line of sight down to the ground is more, that angle is more than space available on my screen. There it goes. So what I've done is I've made another view here, which means it is as if we're turning our head downward a little bit and looking down somewhat towards the ground. So now we are looking down and we can see that little tower. This was the horizon line represented by the balloon, and this is the horizon line visible by the ISS. And these dashed lines represent our 60-degree field of view. I haven't drawn a straight line across here. Don't think it's necessary. There's a very definite curve to this horizon. So that's the ISS. That's the MAGE balloon project. That's what's visible from a commercial airliner. And that's what you see from the top of a 1,000-foot skyscraper. We'll come back out here again. Get a good look at it all. This triangle was an attempt to show the angular drop of the view from the ISS. So we were looking out here, and the angle was such that we weren't even able to see the ground down here. It was below my computer screen, so I had to tilt the view angle down enough to be able to capture some of this. And to put that in the larger picture, that's a circle that represents slice directly through the center of the Earth. That's the amount of it that's visible to the ISS, the International Space Station. This circle is the amount that will be visible to the MAGE project. And this smaller circle is the amount that would be visible from a commercial airliner. Let's put some of these distances into a little larger perspective here. I have taken the circle of visibility from a 1,000-foot skyscraper and superimposed that over Salt Lake City. This yellow circle here, if everything were flat around it, this is what you would see from the top of the 1,000-foot skyscraper. Of course, with all the hills and all, it's not a perfect circle, but we're simplifying. And let's put that in a larger context. There you see the entire planet, and that's what you would see from your 1,000-foot skyscraper. And now let's look at going up to the next level, a commercial airliner. And I've drawn again a circle from a commercial airliner that would be flying directly over Salt Lake City. There we see the field of view of that airliner. That would appear to be the horizon if you had a clear view from your airplane. And based on what we saw in that geometric model I created, under ideal conditions with no clouds on the horizon and with the ability to see a full field of view and have a comparison straight edge to put next to the horizon, it would begin to make out the slightest bit of curve at that elevation. And now let's take a look at the circle for the MAGE balloon project. Now we're looking at a circle for the MAGE balloon project, 39,000 meters, roughly 120,000 feet. This would be the area of visibility, the field of view for that balloon. And as we saw in the geometric model, a definite curve in the horizon would be visible at that elevation. And finally, we're going to look at the amount of the Earth that is seen by the International Space Station. And here we have what is seen by the International Space Station at any one time as it orbits over our planet. This circle here is its extent, its field of view of our planet as it does its orbit. As you can see, it actually sees a relatively small area. There's no way that it shows us an entire hemisphere. We're seeing just a small portion of a hemisphere as it moves over us. So part of the message here is that there's an issue of scale. It is really, really big, Earth, and we are really, really small. And you have to get really, really high to begin to be able to see curvature at the horizon. I think that should be evident from the material I've put together. I want to share one more thing here. I am going to sum up here, and while I'm doing that, I'm going to play this little bit of footage from this video here called New Zealand Earth from Space. What we're seeing is view taken from the International Space Station as it's orbiting and passing over New Zealand. And I'm going to point out that what we're seeing on the right are some of the solar panels of the space station. And in particular, I want to point out that we see that the straight lines of the panels appear straight in the image on the screen, which means there is no barrel distortion from the cameras, as we discussed at the beginning of this video. So what we're seeing here is an accurate representation of reality. The passing of the image through a camera lens is not distorting and causing straight lines to curve or curved lines to straighten. So while that's playing, I will just go back and recap. What is the greatest evidence for a flat Earth? What do we found ourselves on? The greatest evidence is the observation of a flat Earth. This was your opening statement and the foundation for your entire area of research, your entire video series. Not just this one video, but the entire series. If this observation is itself fundamentally flawed, it's as if you have built an entire building on an unstable foundation. The entire building is flawed when that foundation is flawed. So in a sense, if that foundational observation is wrong, is misguided in some way and not correct, then everything else is irrelevant. There's really no need to address anything beyond that when that first assumption is incorrect. Now I am going to continue with this series and go through your videos one by one and address each of your points. But I needed to point out that this entire structure, this entire overarching concept is based on this idea that we observe a flat Earth, that the Earth we actually see is flat. I have discussed only one way of looking at the Earth, which is looking at the horizon. How can I say this? Crossways, looking across at the horizon, as you showed in a few images you posted in your video of a horizon that appeared to be a straight line. I've attempted to show through the geometric models and the images that I've presented here that if the Earth is curved, that horizon would indeed appear to be a straight line. So if we see a straight line, we can't conclude from that it is curved or flat. However, if we go up enough and start to see a curved line, we cannot conclude that it's flat. Elevation is essential in making this observation, and it cannot be conducted from the ground and yield anything useful. I've shown through the geometric model that even from a commercial airliner flying at 33,000 feet, it would be extraordinarily difficult to see the tiny bit of curve that is apparent at that elevation. There is some curve, and under ideal conditions, with the assistance of a straight edge, you would perhaps be able to see it, but that would be really pushing the limit. You have to go quite a bit higher than that. Now, the MAGE balloon project is going to be going up in the next few days. It will be going up high enough that if it succeeds in capturing good quality imagery, we should again be able to see the curve. Other balloons have gone up. Unfortunately, most of them use wide-angle lenses, so they're not helpful. This particular view, and there are many other views from the ISS, does not use a wide-angle lens. There are others that do. Just simply ignore those. They're not useful for this type of observation, for this purpose. They're useful for other purposes. But in the end, we can and we do observe a curved horizon, and we can see it even more clearly even at low altitude if we don't look crossways at it, but rather over it. Every time the sun sets and illuminates the undersides of clouds, geometrically, that's highly probable. That is what we would expect to see on a curved Earth. And in order to justify something like that on a flat Earth, people have to make huge constructs using multiple assumptions that don't add up and don't fit with other natural phenomena, contradict other natural phenomena. Every time we see a boat disappearing over the curve, or do a long distance observation of a mountain that's behind the horizon, it's the same thing. We're looking over a curve towards the horizon, and we're seeing images that conform to the geometry of a sphere. So there are many ways to see the curve. There's not just looking at the straight horizon of the ocean in the distance. And even if we do that, if we can get high enough, we will see the curve as we are right now looking at it over New Zealand. So, Kyle, I will continue with this series, but I think that you need to think hard about whether or not your opening statement for your entire program was correct. You said, what is the greatest evidence for a flat Earth? Greatest evidence is the observation of a flat Earth. No matter how high you fly, straight horizons are what you see. And we are right now flying over New Zealand and seeing a curved horizon.